Hello everyone and welcome to lecture today. Today what I'd like to do is continue from the last lecture, which is go over some more examples of domain and range of multivariable functions. We'll talk about an example in 2D, an example for a function of 3 variables, so in 3D, and then I'll extend to the concept of how we visualize expressions in 3D. So in general in 3D and in 2D. Cool. So let's get into it by going into our first example. So the example that I want to talk about is another function, a multivariable function, where we want to find the domain and range of that multivariable function. So suppose we have the multivariable function f of xy is equal to the natural log of y squared minus x. So you could ask, what is the domain of this function ln of y squared minus x? Remember from last lecture that the domain of a function is the set of all points for the variables x and the variables y for a function of two variables, all points x and y where this function is defined, where it's a nice function. So you want to think about anything and everything that might make this function not defined. And you have to take away all of those points from the actual domain of the function. So looking at this function, y squared minus x is fine. There's no bad things in the y squared minus x. But then you look at this and you see that you have natural log of y squared minus x. And we know that this natural log function has a very severe restriction for what it can be. Right? It's not possible to take the natural log of a negative number, for instance, because natural logarithm function, if you graph it out, ln of u, say, where this axis is the u-axis. Right, this is the function natural log of u. When u is 1, this is 0. And it's only defined for positive values of u. So u equals 0 and u less than 0 are completely out. We can't take the natural log of anything less than or equal to 0. So the domain restriction for this function is that this is the domain. This entire thing has to be greater than 0. So y squared minus x has to be greater than 0. And all of the points where y squared minus x is greater than 0, this is going to be all of the points that allow us to take this function. The function is going to be defined. So this means that y squared is greater than x. If we add x to both sides of this inequality, and we can actually, just like for the previous example, we can go through and make a drawing of what this means. So that the boundary of this inequality is when x is equal to y squared. That's the boundary of this inequality. And the idea is that this is a strict inequality. So unlike the previous example where we had a less than or equals to, so we had that the boundary was reached. With this inequality right here, y squared being strictly less or strictly greater than x squared, y squared cannot equal to x squared. So in order to denote this on our picture, we have to draw out. Okay, so this is the x-axis here. and this is the y-axis. So when we draw out this curve, x equals y squared, we have to do it with a dotted line. This is the curve x equals y squared, and none of these points on this curve are included in the domain, because at each one of these points in this curve, y squared minus x is 0, and therefore you can't take the natural log of 0, so these points can't be included in the domain. They're not included in the domain. But the region that is included in the domain is all points where x is less than y squared, or all of these points right here. Right, and it turns out that this is the domain of the function. It's the correct domain of the function. Now we can write this mathematically by saying that D is equal to the set of points x comma y, or xy, the set of vector points xy, such that y squared is greater than x, or x is less than y squared. This is a nice kind of simplified way of writing this expression, or writing this mathematically, but it's nice to also draw a picture so you can kind of see this. And furthermore, right, we can go through and consider again the range as well for this function. And getting the range, we're going to take this, we're looking here at ln of u. So remember, you think u is equal to y squared minus x, and then our function f then is just ln of u. So u as a value goes from 0, an open interval, 0 on this boundary right here, and then it increases without bound as you move away from this value right here. So it's from 0 to infinity, which means that the natural log has its normal range, which you can kind of see in this picture right here. The natural log function range goes from negative infinity all the way down to negative infinity and up to positive infinity, because for any point here in x, you can find a corresponding point in y from negative infinity to positive infinity. So the range on this interval from 0 to infinity is just going to be the normal range of the natural log function, which is negative infinity to positive infinity. And if we open up a visualization, again, I've included two visualizations, one of them being a Geogebra plot, so Geogebra 3D, and one of them being my custom Python code that I make. You can see exactly our calculation of the domain is completely verified. So the domain of the function, or the set of points where the function is defined in 2D, is exactly that, this parabola right here. Right, so it's on the parabola. Let's see, we can see it right here. This parabola right here. It's the parabola x equals y squared, which is exactly what we calculated before. You see that this function looks exactly like you might expect. It's like kind of like the natural log function, but it's like the natural log function on like parabolas, on a parabola, it's kind of behaving in exactly the same way as a natural log function, where it's going down to infinity as you get closer and closer and closer to that parabola. So here you see the same picture from the Python code that I've plotted, slightly different scanning, or slightly different scaling, but you can see very clearly that there's this, it's kind of going down to infinity at this point. There's a problem with the graphing here at that point. Same thing here, just different scaling. It kind of scales it less, or scales it more extremely. This is neat. It's a kind of a cool example. So we have another example that I'll go over. The next example. The next example is going to be turning the domain and range for a function of 3 variables. So let's say we have a function, we'll say w is equal to f of x, y, z, which is equal to the square root of 9 minus x squared minus y squared minus z squared. So there's another example of a square root type problem. So the first thing we see is that this 9 minus x squared minus y squared minus z squared, this entire term right here always has to be greater than or equal to 0, because we're having taking the square root of this term right here. So because of that, right, u has to be greater than or equal to 0. Otherwise, you won't be able to take the square root. So our domain restriction for this function is that 9 minus x squared minus y squared minus z squared has to be greater than or equal to 0, which is the same thing as the condition. You add x squared plus y squared plus z squared to both sides. It's the condition x squared plus y squared plus z squared is less than or equal to 9. And you might be wondering what this represents, like what points in 3D this represents. But the idea here is that we can go ahead and make a nice kind of plot to kind of figure out exactly what this represents. Now remember, this is a function of 3 variables, so it's going to be, you know, dependent on 3 things, on x, y, z, and t. And because of that, we're going to have 3 separate axes that we have to plot. So this is the x-axis, this is the y-axis going perpendicular to the x-axis, and then this is the z-axis going perpendicular to both the x and y-axes, right? If you So all of these axes are perpendicular to one another. They're all at 90-degree angles to one another in 3D. So if you remember from Calc 3 class, hopefully you do. If you don't, that's okay. We have that there's just like x squared plus y squared is equal to r squared. Where r is the distance away from the origin in 2D, or in the xy plane, we can do the exact same thing in 3D. So for any point, say, the distance out to that point can be called rho. And if the point is at x, y, z, then the distance out to that point, or rho squared, is equal to x squared plus y squared plus z squared. This is our general formula for relating the radius of a sphere to the actual coordinates of the sphere, the points x, y, and z. So what this inequality right here is saying is that rho squared has to be less than or equal to 9, because rho squared is equal to x squared plus y squared plus z squared. So that gives you a restriction that rho has to be less than or equal to 3. Which means that the domain of this function, the natural domain of this function, right, is all points in 3D where the radius is less than or equal to 3. And sure enough, we will be able to graph this out. So I'll just kind of draw a little picture here so you have a picture in your notes. Maybe I can use the circle feature. There we go. So all points in 3D that where rho, the radius, is less than or equal to 3. Right, so this is a sphere of radius 3, say. All of the points inside the sphere of radius 3 are included in the domain of this function. That is exactly what the domain of this function is. Because it's all points that satisfy this thing, the thing under the square root is greater than or equal to 0. Now for the range of this function, we can do the exact same procedure kind of to what we did in 1D, or in 2D. You just again consider the function itself along with what it is in terms of the composition. So remember, we'll say u is this 9 minus x squared minus y squared minus z squared. And the function we're looking at is the square root of u. So what we want to do is figure out where u goes to and from when rho is less than or equal to 3. Or rho is always positive as well, because it's the distance from the origin. So because rho is between 0 and 3, and x squared plus y squared plus z squared is rho squared, u is just 9 minus rho squared. Which means that u is between a high value of or a low value of 0 and a high value of 9. When rho is equal to 0, u is equal to 9, and when rho is equal to 3, u is equal to 0, because you have 9 minus 3 squared, which is 9 minus 9. So that means that u is between 0 and 9, which means that the square root of u is between 0 and the square root of 9, which is equal to 3. So this is exactly equal to the range. R is equal to the interval from 0 to 3. It's saying that this function right here only hits values in that interval from 0 to 3. So there it is. We've solved for the range of the function and the domain of the function. And now what I want to do is kind of visualize this just like before so we can clearly see exactly what I'm talking about. So give me 1 second to open this visualization up. And now this is where things are going to get in some sense a little bit interesting, because I talked about yesterday and I've shown a number of different pictures, so graphs of functions of two variables. Well, here's something that's a little bit interesting. We have that a graph of a function of two variables lives in 3 dimensions, in 3D. So, and let me open up. No, I'll finish the example first, and then I'll kind of. Well, I guess what I'll do is I'll talk about this first because it's important. So before I show my visualization for that example, we want to show the idea here that I'm trying to convey. So if you have from Calc 1, say, function of one variable, right, the graph of a function of one variable lives in 2-dimensional space. You need a second dimension to plot the graph of the function. If you have a function of 2 variables, right, or f of x comma y, we've seen that it's possible to visualize the function of 2 variables very nicely by using 3 perpendicular axes, x-axis, a y-axis, and a z-axis, and then plotting out for every given point in the xy plane, plotting out the value of the function. So say, let's say at this point right here, the value of the function is right here. At this point right here, the value of the function is, say, right here. This point here, say the value of the function is this, and then at this point here, the value of the function is right here. Let's say it kind of looks like a sine on the surface. So we can plot out the surface, and we say that where z is equal to the function of xy, where at every given point, say, every given point x and y, the function value is plotted, and the height of the z-axis, the function is plotted at that xy coordinate, at that value. So at every given xy coordinate, the value of z at that point is exactly given by the value of the function that we have. Let me just fix this up a little bit. So this is what we've seen already, a couple examples of the graph of a function of 2 variables looks like. Well, what does that mean about a function of 3 variables? It means that if we try and graph a function of 3 variables, this graph is going to live in 4-dimensional space. So what you need is a fourth axis. And the problem with visualization of a function of 3 variables is that we don't live in 4D, so we're not able to do this, to visualize this. There is an option though, and that option is what's called doing a density plot of the function. So the idea here is that you plot out a whole bunch of different points and say, let's say the function has a very low value right here at this point. Maybe it's the value of the function is like at a lower value, and then it kind of gradually, rises up to the value of the function gets higher and higher and higher maybe as you move away from the point. So if you plot a whole bunch of points, this is sometimes called a density plot of points, and you color in the points corresponding to the value of the function at those points, you get what's called a density plot. And you can use this tool, right, a density plot, to go through and kind of visualize how a function of 3 variables is behaving. So this specific example that I'm kind of drawing right here is just kind of like a picture illustrating this, that this function is, say, changing as you move in any given direction in 3-dimensional space. So let's see what this looks like for our example. So in this example, we have the following, remember we have this function, and we ended up showing that this function has a domain of all points x squared plus y squared plus z squared less than or equal to 9, or all points where the radius away from the point or away from the origin is equal to 3, or is less than or equal to 3. And the range of this function we found out to be the interval from 0 to 3. So the idea is that we want to kind of plot this out and see what this looks like. We can do this in the following manner. If we look at what the function value is at a given point, say, so this is our function right here, f of x, y, z. And if we say look at when w is equal to a fixed value of c, what this shape looks like. Sure enough, w equals c, which means this is equal to the value of the function at that point, some point x, y, z. So it's c is equal to the square root of 9 minus x squared minus y squared minus z squared. And to get an idea of what this is going to look like, we can rewrite this inequality, or this equality, a little bit by squaring both sides. So we get c squared is equal to 9 minus x squared minus y squared minus z squared. And if I rewrite this a little bit by adding x squared, y squared, and z squared to both sides and subtracting c squared, we get the equation x squared plus y squared plus z squared is equal to 9 minus c squared. And remember, x squared plus y squared plus z squared is equal to, we're calling this rho squared, where rho is the radius from the origin. So that means that for a fixed value of c, rho is equal to the square root of 9 minus c squared. So what that means is that we get a sphere of a radius square root of 9 minus c squared for any value of c, for any fixed value of c. So sure enough, when we go through and we plot this out, say, for different values of c, for argument's sake, we'll take, c equal to a couple different values. Take c equal to, first, just the maximum value, and c is equal to 3, the largest value in the range. Rho is going to be equal to the square root of 9 minus 3 squared, or 9 minus 9, square root of that, which is just 0. C is equal to the largest value in its range. Sorry, not the largest, but the smallest value in its range. We get that rho is equal to the square root of 9 minus 0 squared, which is just equal to the square root of 9, or 3. So this corresponds to c equals 3, and then the value that corresponds to c equals 0 is this circle right here. Let me just I'll center the circle. Or it's not a circle, but sphere. So it's a sphere radius 3. So this is a sphere radius 3. And sure enough, all of these points on the sphere correspond to a c value of 0. So then the idea is that as c gets larger and larger and larger, you're getting closer and closer. The points are getting closer and closer and closer to the inside, or that innermost point, which is the maximum value of our function. So let's see if we can visualize this. So this is the old plot that we visualized for the previous function. So I'm going to run my Python code. I have some custom Python code for making these density plots. I'm going to run the Python code to visualize this function. And sure enough, when we do that, we end up getting this exact picture right here. Oops, sorry, 1 second. Okay, this exact picture right here, where the function is at its minimum value of 0, and you can see here this is clearly a density plot. As you move closer and closer into that origin point, the function is getting higher and higher and higher. It's at its maximum value at the the origin. So x equals 0, y equals 0, z equals 0, or the c value equals 0. And it's at its minimum value when c equals 0. So c equals 3 in the red right here, and c equals 0 in the blue right here. So out on the boundary of this, the function is 0. And as you get closer and closer and closer to the origin, the function gets closer and closer and closer to that maximum value of 3. And you can see very clearly that this is true regardless of how we look at this function, the orientation that we're looking at the function. So this is a very nice picture that shows that the density plot of this function is matching what we predicted before. And the last plot that I want to show you is how to visualize this in Geogebra. So in Geogebra, you can use what are called sliders. And specifically, I have a slider open to visualize that expression, x squared plus y squared plus z squared equals c squared. And we see when c is equal to 0. Oh, sorry, need to change this a little bit. We want to put in here. Should be 9 minus c squared. So when c is equal to 0 here, we're out at the sphere of radius 3. And then as we go through the range and c gets to larger and larger and larger values, right, the sphere is kind of shrinking. So we can go to, when c equals 3, we're at the origin point, and then at any c value in between, all of those points on that surface that you see there are giving you that c value of the function. So when c equals 3, you have the origin point. When c equals 0, all of the points on the circle or the sphere of radius 3 are giving you a value of c equals 0. And then at any other point in that range, in the range of the function, you can kind of visualize that all of the points on that surface, say here, all the points on this surface right here, are giving you a c value of 1.8, or a function value of 1.8. So this is how we visualize functions of 3 variables. We can't do the graph of the function of 3 variables. You can consider what the graph is. It lives in 4-dimensional space, but it's very hard to visualize. So this is going to wrap it up for this lecture. The next lecture we'll talk about traces of multivariable functions, both functions of 3 variables and functions of 4 variables. Specifically, we'll kind of generalize this idea to what are known as level curves and level surfaces. But that's it for lecture today. Thank you very much for tuning in, and I hope you learned something.